Hello everyone, I hope you all are doing well. This side Priya Bhatia. And in this specific video, we will be focusing on our next interesting algorithm in a module of machine learning. Here we will talk about support vector machines. Okay. Again, it's one of the very widely used algorithm because of its, you can say beauty about handling the outliers or detecting, or you can say handling of non-linear data points as well, which was not feasible in the logistic regression scenarios. So you can say it's an advancement or enhancement of that algorithm itself. Everything as an introductory video, I will try to showcase you in a brief manner. Obviously, in this video, we will not go into much of depth part of mathematical intuition. In the upcoming video, we will discuss the maths behind each and every stuff. But in this specific video, I'll just try to demonstrate you the intuition behind SVM. What are the important, you can say, use cases of SVM, where we will heavily use that. What is the intuition of kernel trick? What is the significance of that? What is the default kernel trick method which is used by SVM, which we will refer documentation for that. So please try to understand each and every stuff in a great detail. Again, it might be maths heavy. Some people will feel like that because yes, there is an equation of hyperplane which we will study in this module. So please be prepared for that. And with this, let's get started. So now, whenever we are talking about this support vector machine algorithm, you will observe one of the most important, you can say, beauty about this algorithm is that it is more robust to outliers. So if your data contains too many outliers, in that specific scenario, you can go with this kind of algorithm. So in other words, I can say that the impact of the outliers will be very less when you're applying this SVM model, on top of your data set. Another interesting thing apart from this robustness to the outliers is, again, this algorithm is also beneficial for both the kind of variety of tasks, whether we are talking about a classification task per se, or we are talking about a regression task scenario. In both the scenarios, you will observe that this algorithm is very widely used. So there is something called as SVC, the full form is support vector classifier, and SVR, the full form is support vector regressor, to do the classification and regression task on top of any data, whatever be the problem we want to struggle with. Now, again, you will be able to observe, usually, just like the way I have talked about that in real-time projects in the industry, random forest is one of the most widely used algorithm. Similar to that, we can say that, you will observe that SVM is also very widely used algorithm. In the previous sessions, in the previous modules, we have talked about logistic regression, if you remember. And we have seen that how logistic regression works in order to classify the data points into two categories. For example, what will happen is, here, let's say we will be having two classes. One class belongs to this kind of points are there. And then let's suppose there is another class, you are saying, which belongs to maybe this part, right? So basically, in logistic regression also, we are trying to find out the best fit line. But here, the only major changes that sigmoid function is working on to give us the, you can say, more appropriate result, more accurate results, to give us the predictions of any given data point that we have. Now, there can be two possible lines which can pass from here, which basically classifies these two data points that we have, or two classes that we have. Maybe this one or maybe that one, right? There can be two possible scenarios, or there can be other feasible scenarios as well, like this. Now, if I'll ask you which one is the best one, which one is the best line, maybe let's say this is the line pi 1, this is the line pi 2, this is the line pi 3. So which one is the best line to do a classification task of these two data points? Maybe this is a class A and this is a class B. So you will say that, Priya, in whatever line we will be having a more difference, more distance between the points that we have, right? Maybe this one and this one. So let's suppose that this pi 3 is the line where the distance between class A point and class B point is maximum, let's suppose. So that's the best fitted line which can basically classify between the class A and class B, and maybe pi 3 is the better one, right? As of now, we don't know the exact distance values, but we're considering as an assumption. So same thing is done by support vector machine as well. But there is another difference, which is the major beauty about this algorithm is, if you remember in the logistic regression, I think we had a great talk where we have seen that if the data is linearly separable, when I'm saying linearly separable, the simple meaning is that you can easily able to draw a line like this, which can be easily differentiable and will be easily help us to solve the problem of classification task between the class A and the class B. If the data is linearly separable, in that case, you observe that logistic regression LR works pretty well. Even SVC, support vector classifier, will also work. But the main beauty about this algorithm is that what if your data is non-linearly separable? What if your data is non-linearly separable? So in that case, what will happen is, in that case, logistic regression algorithm LR will not work, but SVC will work. That is where the concept of there is something called as kernel trick came into picture, which is only available in support vector machines, and it will be easily able to classify the two data points which are not linearly separable as well. If there is anyone who is confused between what is the meaning of linearly separable versus non-linearly separable and wants to understand with the visualization per se, so let me just capture one image here to just showcase you what is the significance of the meaning of when I'm saying linearly separable and non-linearly separable. So let me just take one picture and you will be able to understand the context which I want to showcase you here. So I hope you can see this picture pretty well, right? Figure 3 and figure 4. So if I will say the figure 3, this is a linearly separable data because here the curation of a line is very, very easy, right? You can easily able to see, let's say this is a class A that we have, and this is a, let's say we will be having a maybe class A, and here we will be having class B. So it's very easy to create a best fit line which can easily able to classify between the class A and class B, right? But when we're talking about this non-linearly separable data points, right? So in this specific case, you will easily able to observe one thing, that we cannot create a single line per se which will be easily able to distinguish that. How will you create? How will you create? Will you be able to create? How will you create? So the important thing you have to understand here that the data is non-linearly separable. This SVC, this support vector classifier, will also easily able to classify the data points in this specific category also. So now I think it's very easily comfortable with everyone that what is the significance or the interpretation behind the linearly separable data and non-linearly separable data. You can just try to visualize that so that it will be pretty much clear to everyone. Now you must have one question that Priya, like how basically this will be able to classify that in this kind of a category. So as I told you, there is a concept of kernel trick which works. I'll just give you a brief, you can say, context behind this kernel trick also. So what is happening is we have multiple kernel tricks in our SVM classifier. So if I'll just try to showcase you the documentation of that. So just give me a moment. I'll just open the SVM, or you can say SVC classifier documentation. I'll just open that just to showcase you what is the context behind this kernel trick. So if you just go to the documentation, you will be able to see by default the kernel is RBF. I'll talk about these things in a very detail in the upcoming sessions. But one thing which is you have to make sure is that this somehow kernel is helping our model in the support vector machine or support vector classifiers to give us that classification task even for a non-linearly separable data. How will it will be done internally? What kind of function it is executing internally? For that, again, let me show you visually, because visually I think we usually able to understand the context in a better manner. So this is the second image which I have just uploaded, and I think now it is pretty much visible to everyone. Here you will be able to observe one thing. What is happening here? For example, let's say you will be having a 2D data, right? This is also a two-dimensional data. This is the x-axis we have. This is the y-axis we have. So whenever we will be having a two-dimensional data, right, where the data is non-linearly separable, there are multiple kernel functions we have. For example, just now we have seen in the documentation that by default it is RBF. So what is happening is, after applying a kernel trick on this 2D data, it will convert that specific data into higher dimensional space. So now what will happen? This 2D data is converted into 3D data, and now it's very easy to curate a plane. It's not a line. So always remember, when we are working with the two-dimensional data, we always try to curate a line, right? A best fit line. The equation of a line is nothing but y is equals to mx plus c, which we usually write, right? After that, when we are trying to convert that 2D to a 3D data, in that case, we are trying to, talk about a plane. This specific thing is called as a plane. Right? This is a plane that we have, and in this specific plane, if you will be able to observe in this three-dimensional data, we will be able to easily classify between the two data points that we have. One is above the plane, another one is below the plane. I hope you can clearly see that, right? After that, you will also able to observe that with the help of kernel trick, we will be easily able to convert our two-dimensional data into 4D, 5D, ND space as well. 4D, 5D, ND, until or unless we will not able to get a proper, you can say, line or a plane, which we also called as hyperplane. Okay. In the further upcoming dimensions, the same thing you are calling it as an hyperplane. So what is happening is your model is trying to create a hyperplane internally, so that it will be able to classify between the two categories. So the internal intuition behind kernel trick is to convert a lower dimensional data to a higher dimensional data, so that it will be very easy for our model to create a hyperplane for the same. Because creating a line is not feasible, because in a two-dimensional data, it's non-linearly separable. But that is for sure, if we will be able to convert that data set into higher dimensions, we will be able to get easily the hyperplane, which classifies the 2 points, 2 classes that we want to classify. That is the overall idea behind this algorithm. In the upcoming sessions, you will observe that we will try to discuss the maths or mathematical intuition behind this hyperplane only. For example, we know what is the maths behind a line. What is the equation of a line? This is the equation, right? With the help of this equation only, we will try to see what is the equation of a hyperplane, right? How our model will be trying to curate that hyperplane. But this is one of the very widely asked question in an interviews also, that what is the significance of a kernel trick? By default, it's RBF, right? Which is equally valuable for a non-linear based data also. So if an interviewer will ask you that how support vector will be able to classify the non-linearly separable data points, now I think with the help of this session, you will be clearly able to explain that there is a concept of kernel trick internally inside the support vector machines algorithm, where the objective is to convert a lower dimensional data to a higher dimensional data, so that it will be very easy for our model to curate a hyperplane. If the line is not feasible, hyperplane will be feasible, right? There's a maths behind that we will discuss in the upcoming session. One more thing, people can ask you what is the significance of, you can say, support vectors. So there is a term which I will use very frequently in my upcoming sessions called as support vectors. So what is the internal intuition behind that? Support vectors. See, I have a limitation when I'm explaining you the key things. I won't be able to showcase you the high dimensional data in terms of visualization per se. Maybe I'll try to capture few data points. For example, it's a 3D data. You can see X dimension, Y dimension, and Z dimension. But obviously, beyond that, also showcasing you and explaining you will take a bit difficulty. So you should be good in terms of visualization. Whatever things I want to convey, maybe listen it very, very carefully. Then only you will be able to understand the context, right? So what is happening is, for example, when we're talking about a higher dimensions, as you now clearly understood, that our objective is to create a hyperplane on top of this, right? So let's say we will be having a data points available with us, and we want to classify the 2 data points, right? So what is happening is, let's say you will be having one class available here, there are data points available in one of the class, like this, 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 right? So what is happening? This is one of the class data points that we have. And let's assume this is another class data points that we will be having, okay? And what usually happen in curation of the hyperplane is that if you will be able to observe here, the data points that we have, right? The closest data points where the error is, you can say it is actually coinciding with the points, right? This is called as pi 1, let's say. This is called as pi 2. So we usually try to, our model will try to create two separate lines belonging to specific class where the distance between the closest point will approximately equals to 0 or minimum, right? Now, in between that, a new line will be created, which is the plane which we are saying, and this is something which we call as a D. This D should be as maximum as we can curate. So our target is to maximize this value of D. Why? So that you will be able to observe that wider this value of D, which we call as a margin also, by the way. In you will observe mathematical terms, this is something called as a margin. Now, if this value of D will be bigger, it means that there is a separate boundary altogether where the proper classification will be done. So to get that proper classification to be done, right, you will be able to observe that you can say, classes will be defined in two separate categories, and there will be no as such coinciding thing happening here, right? So this is something which is where the hyperplane will be designed, right? The hyperplane will be designed. Now, what is the exact equation of this hyperplane, right? How basically this will work? For example, in the simple line, we have an equation of y is equals to mx plus c, which in general form, we can write it as, you must know, ax plus by plus c is equals to 0. I hope you all know, right? So when you are saying for a simple normal line that we have, the equation is y is equals to mx plus c. So you can write the same equation in a general form as ax plus by plus c is equals to 0. You can ask me, how is that feasible? Do one thing, you can take everything towards the one of the side where you can say mx plus c minus y is equals to 0. So you can observe here, right? Or you can write it as mx minus y plus c is equals to 0. So all these are the coefficients where the value of a is equals to m, the value of b is equals to minus 1, and the value of c is equals to 1. So definitely writing the equation like this way or that way or that way, all these are the same things. Now with the help of these equations of a line, in the next upcoming session, we will try to originate what is the equation of a hyperplane. If you guys have remembered the concepts of mathematical part in our lower classes of 11th and 12th, you must be aware about the equation of a hyperplane and how will it looks like. But because it's an important concept in SVM, because all we are trying to do here is to design a hyperplane only. So I will try to talk about this mathematical part in the upcoming session, and then I think it will be very much clear to everyone. So with this, I hope that whatever intuition I have provided you with respect to the concept of SVM as an introductory video should be pretty much clear to everyone. If you still have any sort of doubts, any issues, please do reach out to me. I will for sure try to resolve it as soon as possible. With this, bye-bye everyone, and happy learning to all.